going to start a stopwatch. Welcome. We are 3 representatives from Waterloo cGEM, and we're going to walk you through Remine, closing the loop for heavy metal waste.
Okay, so throughout the presentation, you'll see some different symbols on each of the slides. So some of these will be representing our 3 sub-teams, so either lab and design, math and modeling, and human practices. And then right next to these symbols will be the specific metal criteria that we are tackling. Okay, so this graphic kind of shows the heavy metal life cycle that we've established. So in our first research session for our project, it was clear that we were aiming to target heavy metal contaminated wastewater, which could lead us in many different directions. So we initially had our mind set on the mining industry, which is number 1, sourcing. This is the foundation of heavy metal extraction required for different applications. So we worked under the assumption that wastewater from this industry was the best option for our proposed solution. We spoke to different stakeholders in mining, however, which helped guide our heavy metal selection process. However, the mining industry just wasn't feasible. This led to a shift in direction to the next point in the heavy metal life cycle, manufacturing. We briefly considered recycling. However, the characteristics and parameters of wastewater from the manufacturing industry proved to be more practical for our system.
So the effects of heavy metals, we are specifically talking about examples like nickel, zinc, copper, cobalt, so on and so forth. They are toxic to humans and to ecosystems, as well as they biomagnify in food chain. And this is to say that higher up the food chain you go, you'll find more of these toxic metals, from starting in smaller organisms to being consumed by larger organisms, so on and so forth. This toxicity is gained all the way through, and it is not helpful for humans, it is harmful for humans. So with these volumes of waste, they are absolutely huge. 4,000 tons per hour of waste are made in the electronics industry alone worldwide. And because of this, we wanted to look at areas in there and think, is there a way of looking at this e-waste, taking these heavy metals that, yes, they are toxic, they are also of use to us, and putting them back in the system for things like metal finishing? Can we collect things like nickel, iron, copper, zinc, to use them for greater purposes than just ending up in our ecosystem?
Now, let's discuss our proposed solution to this problem. Designed to treat dissolved metal ions, Remine is a packed column bioreactor containing cellulose and a fusion protein. The fusion protein is composed of a cellulose binding domain as well as a metal binding domain. As wastewater flows through our packed column, the dissolved metal ions bind to the fusion proteins. By changing the chemical environment of the column, the metal ions can then be recovered into a pure solution for reuse. Additionally, the system is modular in that by using a suite of different metal binding proteins, it can be adapted to the compositions and needs of diverse waste streams. There are several treatment methods currently used in the electronics manufacturing industry. And here is a table that provides a quick overview of them. Chemical precipitation is relatively cheap and easy to use, but generates landfill waste. While ion exchange resins and adsorption recover metals, they are expensive, harder to use, and also cause serious secondary pollution issues. They also recover metals non-specifically, requiring further separation before recycling is possible. Contrary to most of these solutions, Remine has the potential to be both cost-effective and sustainable, as it is composed of natural products. However, the main competitive advantage of our solution is its ability to recover valuable metals using high specificity proteins, essentially remining them for later uses.
Okay, so as mentioned earlier, when our focus was shifted primarily towards mining, we had the opportunity to speak with different stakeholders within the industry, including Brian Montgomery, a lawyer practicing within the field of mining practices and procedures in Ontario. At this point, early in our project timeline, we were focusing specifically on iron because it is the main contaminant in mine tailing ponds, and there's a high level of characterization of iron-binding proteins. However, Brian gave us some examples of a few more valuable metals that may be more beneficial to retrieve as opposed to iron, including nickel, cobalt, and arsenic. So this led us to do our own research on different metals with higher value. And we landed upon copper, iron, and antimony, but we were primarily focusing on copper.
So recovery, not just remediation throughout this project. We're interested in recovery because cleaning the waste and providing accessible metal ions for further application closes the system that we are trying to work with. It's not a matter of just cleaning the water, but it's taking these precious metals, extracting them, and then using them for later use, because mining is extremely dangerous and is not as sustainable as this practice could be with Remine implemented.
Now we're going to discuss a bit of the wet lab plan that we have for our project this year. So the wet lab team's first step was to search literature for metal binding proteins that would be suitable for our system. And we were specifically looking for easy to work with proteins that could be monomeric, cytoplasmic, or periplasmic, but still be able to bind the target metal ions in vitro. Since we were originally aiming to tackle iron waste in mine tailings, we first identified the iron binding proteins FUTA1 and FUTA2. We were later directed away from iron by the human practices subteam because this metal is not particularly toxic or valuable, and because there were also other feasibility issues related to this field. But our strategy for finding these metal binding proteins remained the same as we moved to target copper in metal finishing effluents rather than iron in mining effluents. Using this approach, we identified the copper binding protein COPC, and this is a periplasmic copper binding protein that is very easy to work with and has a number of desirable properties. We constructed some fusion proteins where we connected our copper binding proteins with our cellulose binding proteins so that they would be able to be immobilized in our packed column. In order to make these fusions, we connected the metal binding domain to the cellulose binding domain, cBm2A, using a flexible linker. cBm2A was chosen from the cGEM parts registry for its irreversible binding to cellulose, its cellulose binding activity in acidic pH, and also because of its well-characterized cellulose binding affinities. Furthermore, it has been used in many enzyme purifications and other enzyme fusions previously, and it has been shown to be able to retain cellulose binding activity while in a fusion protein. We also added a his tag to these parts for easy purification of the resulting enzymes. Even though we were unfortunately not able to regain access to our lab this term, we determined some ways to quantify our protein's ability to bind the desired metals using spectrophotometric techniques. We also researched into some different purification methods that would allow us to scale up our system in the future. Lastly, we designed and budgeted for a packed column prototype that we would like to assemble in the lab to demonstrate our proof of concept. I'm now going to spend some time discussing our dry lab work for this term. So the first part of our dry lab work involves rational protein design. So this involves modifying existing proteins so that they can bind metals more effectively. This would be very helpful for our technology because it would make our packed column reactor more efficient at removing metals from wastewater and therefore more economically viable. We specifically focused on the copper 2+ binding protein, COPC. This image shows the binding site of the original unmodified COPC protein. As you can see, the copper 2+ ion has 4 ligands. 3 of these are amino acids, histidine in 2 different places, and also an aspartate, and then also the protein's N-terminus also serves as a ligand. When we engineer metal binding proteins, our main goal is to modify affinity, and this specifically refers to the strength with which the protein binds to the copper metal. And this is useful because if the copper is binding to the protein with more strength, this makes it easier to recover more metal from wastewater with the same amount of protein. We're approaching protein design using an iterative engineering design approach. So first for this is the design phase. So in order to do this, we spent a lot of time reading biochemistry literature, thinking about things, and also just applying our own knowledge of the field to decide which residues we should change in order to increase metal binding affinity. This stage is already complete for one set of proteins, so we've made these modifications. Next is a stage that we can kind of loosely call build to fit into the engineering cycle framework. In this phase, we implement the residue changes that we decided on using a software called Rosetta. Rosetta is a really powerful protein tool, and it allows us to mutate any residues that we like, and then Rosetta is able to consider the effect of this mutation on the overall protein structure and the ability to bind copper. This is really useful because it allows us to check that any amino acid modifications that we've made don't have any huge negative effects on the protein, such as causing folding issues. This stage is also complete for the first set of protein candidates. Lastly comes the test phase. So in this phase, we use molecular dynamics to determine thermodynamic and kinetic parameters of the proteins that we've designed and built. This allows us to determine whether the changes that we've made have actually improved the protein in the way that we've hypothesized. And since this is an engineering design cycle, we're able to take the results of the test phase and then iterate back and go through the design and build phases again with more information. So here are some examples of our engineered proteins. So on the left, you can see this is the original copc active site that I showed a few slides ago. And then in the design phase, one modification that we came up with is that it could be helpful to change residue 105, which is originally an aspartate, to be a histidine or a glutamate. So these are the changes that you see in the middle and rightmost figures. And you can see that residue 105 has been changed from an aspartate in the leftmost residue to a histidine in the middle and to a glutamate in the right. So for the build phase, we were able to use Rosetta to make these desired mutations and look at the effects on the protein structure. And while it does this, Rosetta provides what it calls an energy score for each of these structures, where the more negative numbers are more stable. So you can see that the energy scores for all three of these proteins are very similar. And this confirms that the changes that we've made haven't had any significant negative effects on the protein stability, meaning that they probably won't have any major folding issues. So now let's discuss molecular dynamics. So as I mentioned earlier, molecular dynamics makes up the testing stage of our engineering design cycle. Molecular dynamics lets us study and validate our modified proteins in more detail than is possible with Rosetta. And molecular dynamics, at least broadly, it works by simulating the interactions of individual molecules at a molecular level over time. And in order to do this, we're using a software that's called GROMACS. So currently for molecular dynamics, we're in the data collection stage. So we've set up our system, and now we just want to use this system to be able to compute the parameters of interest. So on the right, we have a picture of our GROMACS input file. So you can see that the protein is shown in green, the copper ion is in purple, and then there's a huge number of just water molecules all over the place. And this, this kind of simulates what it would be like to have a protein and a copper ion in an aqueous solution. And to put it simply, what we're going to do next is just allow all of these molecules and the protein and the copper ion to bump into each other, and we're going to be able to see what happens. And by doing that, this will allow us to compute binding affinities and kinetic parameters for our desired protein. And these values are useful because we can compare our original copc with our newly designed proteins, and then we can determine whether or not our modifications were helpful. The parameters determined from molecular dynamics will also be very useful for process design. We can take the parameters that we calculate using molecular dynamics and then put them into our industrial process model, and this will allow us to determine the effects of our improved protein, not only at a molecular scale, but on the scale of our entire large industrial process. So this leads us into process design, which is the second major part of our dry lab work. As we mentioned earlier in the presentation, we plan to build a packed column reactor to treat our metal-containing waste streams, and I've shown just an example of what this could look like in the top right corner. The column will be filled with cellulose beads, and our fusion protein will stick to the surface of these beads, allowing it to trap copper as the wastewater passes through. But this leaves kind of one big question, and that is, how do we actually go about designing our packed column reactor. So to do this, we're going to use a combination of modeling and engineering design approaches. We'll be considering things like fluid dynamics, mass transfer, protein-metal interactions, and much more. So first, as with any model, we needed to identify our model inputs. So these are pieces of information that we collected from literature, from molecular dynamics, and from human practices work to basically identify the problem that we need to solve and figure out the requirements of the solution that would fit. So some examples of inputs were the volume and metal concentration of the waste that we would want to treat from a particular factory or industry, the permitted metal concentration that can be released into the environment so that we know how much metal we need to remove, the way that the protein and cellulose interact, the way that the protein and metal interact, and so on. We'll then use our modeling and design process to come up with a final reactor design that meets the criteria we provided. This will involve the size and the shape of the reactor. So like the radius and diameter, will this be a reactor that's 10 meters in diameter and 100 meters long, or much bigger or much smaller? And we can also determine the amount of liquid that would pass through at a given time. So 100 liters an hour, 10 liters an hour, 1,000,000 liters an hour, and so on. From these results, we can think about how much it might cost to build our reactor, and then whether or not this would actually be economically feasible. I'll now go over some of the details of our model. So the first thing that we needed to do was to make an equation that would describe how fast copper ions would bind to COP-C, which is our copper binding protein. So in this equation here, M represents the concentration of copper, and dm by dt is the rate of change of the concentration of copper. So this equation describes, on the left side, we have the rate of change of copper, and on the right side, we have an expression in terms of the copper concentration. So for any copper concentration, we're able to see how fast it's going to be removed from the solution by COP-C. However, we also need to account for our reactor as a whole, the way that liquid flows through it, and the way that copper concentration will be different at different points within our large packed column reactor. So we can imagine, for example, that the copper concentration would be very high at the top of the reactor where we feed our solution in. And as that kind of percolates through the reactor, we can imagine that the copper concentration would decrease as more and more copper gets bound to the COP-C and removed from solution. So in order to do this, we take the equation from our last slide and we've added some more terms in here to account for advection and diffusion. Simply put, diffusion refers to the way that any metal ions would naturally move from areas of high to low concentration, and advection refers to the way that copper ions are carried by flowing fluid. So now that we have developed the equations to use, we just need to finalize our reactor's design. So HP has determined that we should aim to treat wastewaters containing about 30 milligrams of liter of copper 2+, because these are relevant waste concentrations in industry. And they also found that the permissible concentration of copper that can be released into the environment is 1.3 milligrams per liter. So this means that we need our system to be able to reduce the copper concentration by this much in order to be feasible in industry. And from this, our modeling will allow us to determine the reactor size and flow rate and so on that we should use in order to go about achieving this goal.
Now to look at some of the public endeavors we took on as a team. One such endeavor was public engagement education, specifically for other iGEM teams. We had a few. We figured this would be the best to focus on for cGEM. Our lab team has compiled educational presentations that can help other iGEM teams on onboarding new members, as well as the fact that at the end, they have accompanying Kahoots to test your knowledge and have some fun.
Okay, so the next thing that HP kind of focused on was community research. So the competition allows for teams to explore concepts outside of the project in order to contribute to excellence in another area. Waterloo iGEM chose to address barriers to equity and representation within STEM workplaces from various perspectives. Intersectionality refers to the interconnectedness of our social identities like race, gender, sexuality, ability, and more. These diverse identities create interdependent systems of prejudice and discrimination. The way to remember this is that our whole identity is not simply the sum of its parts. It's complex than that. We are actively conducting research that includes real-world anecdotes of prejudice and discrimination in STEM spaces that folks in all walks of life have experienced as a way to provide evidence for the barriers that prevent underrepresented groups from participating, learning, and connecting with STEM. We also wanted to make iGEM wikis more accessible to more people, so we are compiling a handbook of tools and guidelines iGEM teams can use to ensure that their wikis are accessible. Additionally, we are creating an open source accessibility toolbar that any iGEM team can easily add to their wiki.
This year, we have two ongoing collaborations with two different iGEM teams. And the first of these is with Ohio State University. This was a really exciting opportunity to continue working with Ohio State after we began this last year. And specifically this year, Ohio State is developing some tools for biocontainment, and we're providing some support for their model development and implementation as they use mathematical tools to describe these biocontainment situations. We're also collaborating with the University of Tübingen in Germany, which is a really exciting opportunity. This is the first year that we've worked for them. And they are improving a manganese binding protein for a biosensor application. And although their application is quite a lot different than ours, they're using a lot of the same strategies in terms of rational protein design and molecular dynamics. So there's a lot of good opportunities to be able to collaborate and share our successes and failures in those areas.
So what is the future of Remind? As we said, we are currently working in electronics manufacturing, but we do believe with the foundation that we have built, as well as the work we continue to move forward with, we could put it in all areas of expertise, moving it to sourcing, recycling, disposal, for example. The possibilities are really endless. So thank you for coming to our presentation. We'd like to briefly thank our sponsors, as well as our advisors and consultants, and remind you that if you would like to follow us further, make sure you keep up with Waterloo iGEM. Thank you.